To learn how to simulate Verilog code by hand, we're going to start by looking at the Verilog standard to find out what it says about how a Verilog simulator should function. The relevant chapter is chapter 11, titled Scheduling Semantics. An HDL has to be a parallel programming language. The execution of certain language constructs is defined by parallel execution of blocks or processes. It is important to understand what execution order is guaranteed and what execution order is indeterminate. The semantics of Verilog are defined for simulation. Verilog was not meant to be used to synthesize digital circuits. Quartus does this, but it's not the primary purpose of Verilog, and that's why you can sometimes feel there's a bit of a mismatch between what Verilog was designed for and how you use it in Quartus. Verilog existed well before FPGAs did, and the purpose of Verilog was to be able to debug or check whether a digital circuit would function correctly. The Verilog HDL is defined in terms of a discrete event execution model. Basically, this means we simulate time in discrete increments. It is interesting and important to note that there is a great deal of choice in the definitions that follow, and differences in some details of execution are to be expected between different simulators. In addition, Verilog simulators are free to use different algorithms from those described in this clause, provided the user visible effect is consistent with the reference model. So before in this course, when we have been talking about not knowing the order of execution, it's due to this part of the standard we know that different simulators are free to do things in different ways. A design consists of connected threads of execution or processes. So I like to explain this by we have hired a bunch of friends and each friend does one thing. And with many friends, we can have many threads of execution or processes. Examples of processes that we have seen are modules, initial and always blocks, and continuous assignments, which are assign statements. Remember, a process is basically a block, like an initial or always block or an assign statement or so forth. Another definition is an update event, and every change in value of a net or variable in the circuit being simulated, as well as the named event, is considered an update event. A net is a wire or a reg, and a variable is like an integer. So every time a net or a variable changes, it's considered an update event. Processes are sensitive to update events. So a process could be an always block. So an always block is sensitive to, and an update event is when a variable or net changes. And this makes sense. If I have always at x, then when x changes, we've been saying that the always block gets called. So that's because processes are sensitive to update events. When an update event is executed, all the processes that are sensitive to that event are evaluated in an arbitrary order. Remember, we keep saying that Verilog simulators are free to choose the order of execution. It's written in the standard that they have that choice. The evaluation of a process is also an event known as an evaluation event. So we have update events and evaluation events. So an evaluation event is when, for example, an always block gets executed, and an update event is when a net or variable changes value. In addition to events, another key aspect of a simulator is time. The term simulation time is used to refer to the time value maintained by the simulator to model the actual time it would take for the circuit being simulated. The term time is used interchangeably with simulation time in this clause. So in particular, we don't care about the actual time on your watch. We don't care about how long the simulator takes to function. We just care about what is the current time that we are simulating in the digital circuit. Events can occur at different times. In order to keep track of the events and to make sure they are processed in the correct order, the events are kept on an event queue, ordered by simulation time. Putting an event on the queue is called scheduling an event, and we're going to look carefully at this event queue. It's called the stratified event queue. The stratified event queue is segmented into 5 different regions. Events are added to any of the 5 regions, but are only removed from the active region. So keep this in mind, we'll explain it soon. This is the stratified event queue. We have got active events. They occur at the current simulation time and they can be processed in any order. So the active events are what we are actively doing right now if we were simulating things by hand. Inactive events occur at the current simulation time, but shall be processed after all the active events are processed. So here we have orders of priority. We might have 2 different things to do at the current simulation time, but the active ones get priority over the inactive ones. Basically, we end up with an inactive event if we have got a #0 in our code, a delay of 0. That forces what follows it to be put on the inactive event queue, as we'll see later. Non-blocking assign updates have got their own slot. They're events that have been evaluated during some previous simulation time, but shall be assigned at this simulation time after all the active and inactive events are processed. So if we have created a transport delay, for example, using a non-blocking assignment, then that means that we have created a to-do note that when it comes round to the correct simulation time, that's placed in this non-blocking assign update, and that will occur after all active and inactive events have taken place. So in fact, we have got 3 priority queues here. First active, then inactive, then non-blocking. And it's important to note that when we're processing active events or inactive events, etc., then they can trigger more events. And so you can end up that something in the non-blocking assign queue has to wait a long time before it gets processed, because when we're processing the active events, they can generate more active events or more inactive events. And only until all those events and all those events that they generate that are active or inactive are completed do we start doing the non-blocking assign update queue. Monitor events shall be processed after all the active, inactive, and non-blocking assign update events. So after we've done everything we possibly can at the current simulation time, then we execute the strobe and monitor commands to print out the final values at the current time step. Finally, we have the future events that occur at some future simulation time. So this is primarily when we have got delays in our circuit. So at the current simulation time, we can execute a statement that tells us we have to wait until the future to do something. We could also just have a #5 or something in there that also tells us to wait till the future. Future events are divided into future inactive events and future non-blocking assignment update events. So events in the future can either end up here when they're ready to be processed or end up here when they're ready to be processed, depending on their priorities, as we'll see subsequently. And just as a quick note, even though it says previous simulation time, that could also be the current time. So if at the current time we come across a non-blocking assignment, then we evaluate that assignment, we evaluate the right-hand side, and then we place in the non-blocking event queue a to-do note telling us to update the left-hand side with the computed value of the right-hand side when we've done everything else. So it's placed in here. The processing of all the active events is called a simulation cycle. The freedom to choose any active event for immediate processing is an essential source of nondeterminism in the Veriloghdl. We often have race conditions. We are supposed to write code so that the final result does not matter on the race conditions. Either way it gets evaluated leads to the same correct answer that we're interested in. An explicit zero delay, #0, requires that the process, remember before a process could be an always block or an initial block. So whatever the process is, if we encounter a #0, then we need to suspend the current process and we have to add what comes next to the inactive events. Here's the inactive events, because we have to finish all active events before we start processing the inactive events. That's what #0 causes us to do. If we are executing the process and come across a #0, we stop and wait for all our other friends who are executing all the other processes. They have to finish all their active events, and only when they finished all their active events do we move on past the #0. So that gets implemented by adding this process to the inactive events queue here. If we want to get pedantic with the terminology, then when we encounter a #0, we suspend it, we add the process to the inactive event queue so that the process is resumed in the next simulation cycle in the current time. So we don't increment time, but one simulation cycle is when we finish all active events. Once we've finished all active events, we'll see presently that all the inactive events get copied and they to the active events queue, or they get moved, not copied. They get moved from inactive events to active events. And then this means that all the processes that were paused, when they get moved to the active events, they then resume their execution straight after the #0 statement. A non-blocking assignment, and remember a non-blocking assignment is simply less than equals. So a non-blocking assignment creates a non-blocking assign update event. That's up here. And it's scheduled for either the current or a later simulation time. So if we just have a non-blocking statement ordinarily, it would be scheduled for the current simulation time, but because it's placed in the non-blocking assign update queue, it won't get executed until we finished all the active events and finished all the inactive events, and only then are the non-blocking events processed. If we created a transport delay, then it would actually go into a future non-blocking assignment update queue here, because we have to wait until we get to this later simulation time as determined by the transport delay before the future non-blocking assignment gets moved to an actual non-blocking assignment to be done after all the active and inactive events have been done for that relevant simulation time. The monitor and strobe commands create monitor events for their arguments. The monitor events, remember, is right here. These events are continuously re-enabled in every successive time step. The monitor events are unique in that they cannot create any other events. So all these events can, when they get executed, create their own events that go under the respective queues, the relevant queues. But monitor events don't create any events. So at the current simulation time, when we've done absolutely everything we can in all these three queues, then we do the monitor events. That is, we print out everything we need to print out based on what strobes and monitors we encountered, and then we're done. Then we're finished with the current simulation time, and we increment simulation time after that. When going through this pseudocode that helps reinforce what I was saying before, we have to keep in mind the priorities. We first have our active events, then we have our inactive events, then we have our non-blocking events, then we have our monitor events, and then we've got our future events. So while there are still events, so if there are no events, then presumably we end the simulation completely. So while there are events, we look to see, are there any active events? If there are active events, then we grab any active event. Order doesn't matter. We don't have to grab the first event on the queue. We just grab any active event. And down here we'll look at presently. It overflows onto the next page. But basically we then process that event. Put simply, we process that event. If there are no active events, then we ask, are there any inactive events? If there are inactive events, then we transfer all inactive events to the active event queue and repeat. If there are no active events and no inactive events, but if there are non-blocking events, then we transfer all those non-blocking events to the active queue and then repeat, go back to the start. If there are no active, no inactive, and no non-blocking, we ask, are there any monitor events? If there are monitor events, then we activate the monitor events. Technically, they get moved to the active event queue, and then we do them. And monitor events are unique in that they can't trigger any more events. So once we've done the monitor events in the next cycle, then we're done for this time instance. So we then finally get to the point where there are no active, no inactive, no non-blocking, and no monitor events. We're completely done for the current simulation time, so we advance time to the next event time. And remember, we have a future event queue. So when we finished all the current events, we look at our future event queue. We find when's the earliest event in the future we have to do something at. We advance our simulation time to that event time, and we activate all the inactive events for that time there. And although they haven't written it, you take any future non-blocking assignments for that time step and move them to the current non-blocking assignment event queue. So to summarize, we do all active events, then the inactive events become active events, and we do all active events again. And we keep doing this, so if an active event generates an inactive event, then when we finished all the active events, we'll find there are some inactive events again. So we go back, put them into the active event queue and do all of those. And we keep doing this until there are no more active or inactive events. Then we look to see if there are any non-blocking events. If there are, they become active, and the same thing occurs as before, do all the active events. Then the inactive events become active events. And when there are no active or inactive events left, then we do any non-blocking events that may have been generated in the course of doing the second round of active and inactive events, etc. Finally, when we've done everything we can, we do our monitor statements and then we advance time. Let's now look a bit more closely at processing active events. So we have an active event, and it could either be an update event, which means a net or variable has changed value, or it could be an evaluation event, meaning we need to evaluate, for example, an always block. So if it's an update event, if the event is to, for example, set x equal to 5, then we update the object, so we actually make x equal to 5, and then we add evaluation events for all the sensitive processes to the event queue. So in plain English, once I've updated x to be 5, I look to see, are there any always statements that should be triggered by the change in x that I have made. And all the processes that need to be triggered, all the always at x statements that need to be done, they get added to the current active event queue. Otherwise, if the process to be evaluated is an evaluation event, we need to run an initial block or an always block or an assign statement, then we just start evaluating the process. And when evaluating the process, we are likely to come across various events that are generated in that process. In an always block, we're likely to do assignments to variables, for example, that would trigger update events. So when evaluating a process, we then get a bunch of update events that we add to the event queue. Importantly, there is some level of determinism. The standard guarantees a certain scheduling order. Statements within a begin-end block shall be executed in the order in which they appear in that begin-end block. However, note that execution of statements in a particular begin-end block can be suspended in favour of other processes in the model. So the only guarantee is that the statements within a begin-end block will be done in that order. Maybe something else happens in between the processing of the statements in the begin-end block, but at least they will be done in the correct order. In no case shall the statements in a begin-end block be executed in any order other than in which they appear in the source. We have another guarantee for non-blocking assignments. They will be performed in the order the statements were executed. So for example, in this example here, we guaranteed that at the end of this block, A is going to be equal to 1. Even though we have non-blocking statements and they go onto the non-blocking event queue, we have got the order in which they're executed being guaranteed because they're between begin and an end here. Precisely, when this block is executed, there will be 2 events added to the non-blocking assign update queue. The previous rule requires that they be entered on the queue in source order. So first A takes the value 0, then A takes the value 1. These will be placed on the queue in that order. And this rule, rule B, requires that they be taken from the queue and performed in source order as well, because they're between begin and ends. Hence, at the end of simulation time 0, the variable A will first be assigned 0 and then assigned 1. That order is guaranteed. Interestingly, that's about the only guarantee on order of execution. The rest we've got nondeterminism and race conditions. One source of nondeterminism is the fact that active events can be taken off the queue and processed in any order. Another source of nondeterminism is that statements without time control constructs in behavioural blocks do not have to be executed as one event. What does that mean? Well, time control statements are the hash expression and the @ expression constructs. Remember, the hash is for delays and the @ is usually used in an always statement. You could actually use it on its own. So at any time while evaluating a behavioural statement, the simulator may suspend execution and place the partially completed event as a pending active event on the event queue. The effect of this is to allow the interleaving of process execution, although the order of interleaved execution is non-deterministic and not under the control of the user. Put simply, this is just saying what we've said before. If I have got one friend doing one process and another friend doing the other process, then even if they have to take it in turns, we can't have 2 friends working at the same time, then there's no guarantee that the first friend will finish and then the second friend takes off and does the tasks assigned for the second friend. It could be that the first friend does 2 things, then the second friend does 1, then the first one does 1 more thing, then the second friend does 3 things, etc. You can have interleaving. The Verilog simulator is free to interleave the execution of different blocks as it sees fit. The only guarantee we have is that within a begin-end statement, the statements are done sequentially, but other things might be done in between 2 different statements in the same begin-end block. To elaborate, we have an example of race conditions here. The assign block, we have one friend doing this. The friend is going to watch Q, and whenever Q changes its value, we'll assign the value of Q to P. That's what one friend is doing. Another friend is doing this initial block. So the second friend starts, assigns 1 to Q. That will place an event on the queue to execute this assign statement at some stage. The #1 here means that in terms of there are no more active events coming from this particular process. So we've finished here. So what happens is that the only thing left to do is to assign P the value of 1. So then we move then we move on to simulation time 1, where P and Q are both 1. Now we have Q equals to 0 and also a $display P. So after this Q equals to 0, there are two things we need to do. We need to do the assign and we need to do the display. And here's a race condition. Depending on whether we do the display first or the assign first, we'll get out either a 1 or a 0. The simulator is correct in displaying either a 1 or a 0. The assignment of 0 to Q enables an update event for P. The simulator may either continue and execute the display task or execute the update for P followed by the display task. Exactly what we said before. There are 2 more pages left of this chapter, but in many ways what's written here we can just figure out. So I'm going to go through some examples now, and if at any time you want more details, you can of course refer back to here or look up the actual standard on the internet. You can come back and look up if you want more details, but it's fairly self-explanatory, I feel. So we're now going to skip this, and we're going to skip this page, and we're going to move on and just look at how to simulate some Verilog code by hand. We have some Verilog code here. It doesn't make too much sense. It's just there for us to learn how to simulate Verilog code by hand. So we need to keep track of the current simulation time, and time starts at time 0. We also need to keep track of the contents of all the nets, so all the wires and wedges and any variables. We don't have any integer i's around here or anything. So we've got A, B, C and D that we need to keep track of. If you like, we can draw these delimiters down here. It's just like bench checking any other computer program actually. Technically, all nets start off in the don't know state at the start of Verilog simulation time. We have got a module here, and intuitively we just pretend that the code in here is inserted into here. That's sort of the simplest way of doing these simulations in here. We've got our module test here that contains a continuous assignment. So that's one process where you imagine we have a friend that is monitoring the right hand side, and whenever it changes it will update D. We have another friend set to do this process, another friend set to do this, and another friend set to do this. So I've got 1, 2, 3, 4 friends basically, or 5 if you count this assign statement here. So actually we've got 5 friends looking out for things to do. Okay, so we start. There's nothing to do here initially because everything's initialized to don't know. We start our module test, and again nothing to do here. We start with the begin block. So this is one of the things we could do initially. This is another thing we could do initially, and this is a third thing we could do initially. And there's indeterminacy. It's up to us to work out whether to do this first, or this first. We do have to finish doing all these 3 things before we advance simulation time. And indeed, since this is something that is already active, I have to finish all the active things before moving on to the inactive things. So there's a little bit of determinacy, but we can choose whether to start here, here, or here. Let's just do the easiest thing and start doing what we see first, which is set A equal to 0. So over here, I mark A equal to 0. A has changed. That's an update event. And so if A has changed, then that triggers a change here, technically up here. And it triggers a change here. So straight after having done this statement here, I now have got two more active things to do. One active thing to do is to do this assignment here. Another active thing to do is this assignment here. And I'm free to decide whether to next do this, or to do this, or to do this, or in fact to do this, or to do this. So we have lots of things we can be doing, and we just pick any of the active things to do next, and it doesn't matter. If the program's written properly, then it should not matter what the final answer is. Sorry, it should not matter the order in which we execute the things. Any final answer that matters should not depend on the precise order of execution if it cannot be guaranteed by the Verilog simulator. So let me just do the easiest thing. I don't have to. I want to emphasize that I could do this or this or this. I'm just going to do this. I'm allowed to do that. So the next thing I do is I set C equal to 1. So I set C equal to 1 over here, and I've now done this instruction as well. As soon as C gets updated, that alerts us to the fact that we also have to process this event here. We have to run this process, but we already have a marker. We already have a to-do note to do this. So had I already done this assign statement before, I'd have to do it again when I change the value of C. But since we decided not to do the assign statement first, then I just have a to-do note to do it, and I can do it, well, I can do it now, or I can do it after the monitor, or after this non-blocking assignment, or after this assignment up here. In terms of this process though, it's going to be suspended. We have a #1 here, so we don't continue any further. We wait at this point until we update time to 1. So we've finished doing as much as we can of this block. Let's move on to this block. Again, we don't have to. We can do any active event, but let's move on to this block. This sets up a monitor statement, and the monitor statement has its own special event queue that guarantees that it will be the last thing that happens at the end of each simulation time. So we're just going to remember that at the end of every simulation time, if any of A, B, C or D have changed, we need to print out the numbers A, B, C and D. Moving on, this is another active event. The active event is actually technically to evaluate the right-hand side. Now, in a more complicated example, if the right-hand side was something like A plus B, we'd have to look at the values of A and B, we'd have to evaluate A plus B, and we'd create a to-do note saying, update C to the value that we computed. In this case, the right-hand side's a constant, so we don't have to do any calculation, but we do need to have a to-do note of setting C to be equal to 0 at the end of the current simulation time. So wherever you like to have your to-do notes, at the current simulation time of 0, we have a non-blocking C takes the value of 0. And I just want to emphasize that if I had C is assigned something like A plus B, I would have to evaluate A plus B, and whatever that came to, that's the number I store here. So I don't store A plus B in my to-do list. I never do that. I evaluate the right-hand side and just store the answer in my to-do list here. Now that I've done this, I come to a #2. This means that we pause the execution of this process until we get to simulation time 2. So we paused here. So what active events do we have? Remember, a computer will be storing all the active events and inactive events and non-blocking events in different queues. For us humans, for short programs at least, we can just keep on going back to the beginning and running our eye down it and reminding ourselves what we have to do. So go back to the beginning. We have to do this assign statement. Assign y to not x. Where does this come from? Well, here x is actually A and y is actually B. So basically we have got set B to be not A. So, okay, let's do this one next. Set B to be not A. In our table, we find A is 0, so B becomes 1. As soon as I update B, I check my code to see if anything else needs to be updated in response to B changing. I have an assign statement here, but no, that doesn't get triggered. Same in here, this doesn't get triggered. This one does not get triggered because B does not appear on the right hand side, and I don't have any more always blocks. So I'm good, nothing happens here. Except of course, because A and B and C have changed, then we need to do this monitor business by the end. Okay, so we've done this and this. We haven't done this yet. We have to assign D to A exclusive OR C. So having a look across here, A is 0, C is 1, so in the exclusive OR then we get a 1, so D becomes 1. Again, I should emphasize, had we chosen a different order, then maybe initially this assign statement would have assigned D to be A exclusive OR C when C was still don't know. Then D would have become don't know. But then when we processed another event, C would have changed again. C would have finally become 1. Then we get to do the assign statement a second time at simulation time 0, and then it would have become correct. At this point in time, we've done all the active events, and so we move on to the, well, technically we have to look for inactive events, but they only occur if there's a #0 everywhere, and many people recommend not to use a #0. It's just you might find some Verilog code that uses it. So there's no #0 here, so we don't have to worry about inactive events. We just have active events and non-blocking events. Because we've done all the active events we can up until this point here at the current simulation time, we now move on to the non-blocking events. So all the non-blocking events now become active events. We only have a single non-blocking event, but that becomes an active event. The active event is C equals to 0. And so we do that. We set C equal to 0. As soon as we change the value of any variable, in this case we've changed the value of C, we need to look to see if that triggers anything. Are there any assignment statements or always statements that get triggered by C changing? And we find that yes, we have this assignment. So now this assignment becomes active. And so we need to do all the active assignments. In this case, so this has become active. It became this active event. We've done that, but that created a new active event. That created the new active event, D equals A exclusive OR C. There are no other active events, just this one. So we update the value of D. D is A exclusive OR C. 0 exclusive OR 0 is 0. Finally, so D's changed. We look through all the assigns and always statements. We find that D changing does not update, does not trigger the update of anything else. And so therefore, we've done everything we can at simulation time 0, except for the monitor statement. The monitor statement now gets called, and we print out the value of A, B, C, D, because they've changed. We get 0, 1, 0, 0. Finally, we come to incrementing simulation time. We move on to time point 1. If we were smart, we should look to see what the next time point is. We could just increment 1 and keep going, but if I had a #10 and #100 everywhere, I don't want to change time to 1, find there's nothing to do, change it to 2, find there's nothing to do. I just look through my code to find out what the next time, what the next instance in time we have something to do is at. In this case, we have a delay of 1 unit, so it is appropriate that we move on to just time point 1 because there's something to do at time 1. So I've incremented time. We still have all our three processes here. I've got one process here, another process here, but this monitor's sort of been done. We've executed the monitor statement. That's created a monitor event that's ongoing. And then we've got this one here too, which at the moment is stuck here. This one is stuck right here. And we do have two more processes, but they depend on a change to the right-hand side, triggering them to do something, where of course this is related to that. Okay, so at time event 1, the only thing to do is to start executing from here. So our next active event is to make a equal to 1. So I set a equal to 1. I've made a change to a. I immediately ask, does that trigger anything else? Well, yes, it triggers this assign statement here, and it triggers this assign statement up here by this instantiation of the module here. So I now have two active events. One active event is this assign statement. The other active event is this assign statement. We are free to choose any order we want. Let's do this active event first. D equals A exclusive or C. A is 1, C is 0, so D becomes 1. Does changing D trigger anything else? No, it doesn't. Then we do this assign statement here. B is assigned the value of not A. B takes the value of not A. Does changing B trigger anything? No, it doesn't. So we're now done at this current simulation time, except for the monitor statement. And so because at least one of A, B, C, and D has changed, we're going to get something printed out from this monitor statement. And this time, what's going to be printed out is 1, 0, 0, 1. We can then move on to the next simulation time. So draw a line here, move on to simulation time 2. Same story at simulation time 2. We're currently paused here, and we're currently paused here. Once we reach simulation time 2, we can continue executing from here to do this. We can continue executing from here to do these statements. And we also have to remember that as soon as A or C changes, this will be queued up. And as soon as A changes, this will be queued up. And at the end of the simulation time, we have a monitor statement. So we're free to choose which one to do first. Let me just do this one first. I set C equal to 1. And then I finished this process here. So I've got nothing more to do for this process here. C has changed. Does that trigger anything? Yes, it does. It triggers this assign statement here. Let's just do this assign statement now before we forget. So let D equal to A exclusive or C. A is 1, C is 1, so D becomes 0. Does changing D trigger something? No, it doesn't. So we've done the assign statement. We've finished the process here. We know to do a monitor at the end of things. That just leaves this process here. I have A non-blocking assigned to 0, so I create a to-do list at time 2. I am to set A equal to, non-blocking equal to, if you like, 0. But I don't do it until I've done all the other active and inactive events. Then and only then do I update A. Is there anything else I can do? Well, yes. I've got this statement here to do next. If A, so remember, a 0 is false and any other value is true. So we're asking if is A 0 or non-zero here. What's the value of A? So the key point is, if we have a look over here, the value of A is equal to 1. Sure, we had this statement up here, but that just creates a to-do note. We haven't actually done it yet. So the value of A right now is 1. So if 1 is non-zero, so that's true. So we're actually going to print out the word true. True gets displayed. We move on. We finish this process now. So we've done this one. We have done this one. We know to print out the monitor. There's nothing pending here. There's nothing pending here. So there's no more active events. No inactive events because we don't have a #0 anywhere. But we do have a non-blocking event here that we can now take care of because there's nothing else left to do at simulation time 2. So this non-blocking event says we have to assign A the value of 0. So cross that off, set A equal to 0. Does changing A trigger anything? Yes, it triggers this assign statement, and via this module instantiation, it triggers this assign statement here. We can do them in any order. Let's do the assign D first. D equals A exclusive or C. A is 0, C is 1, so that makes D equal to 1. And we've done this one. We've got assign B equals not A, so that means B takes the value 1. And finally, our monitor statement prints this out, and we get 0, 1, 1, 1. At this point, we've done absolutely everything, and so we finished simulating this Verilog code by hand. If you want more practice at this, the way you do it is you make up some Verilog code, you run it on a Verilog simulator, you make sure you put display statements everywhere you can. So inside any process, you can add display statements after every line so you can see where you are. Inside any always block, you can add a display statement so you know when the always block gets triggered. If you prefer, you can rewrite assign statements as always blocks, so then you can add a display statement so you can figure out when the Verilog simulator is calling each part of your code. You can then go away and try to do the the desk check yourself, like we've done here, and you can compare it to when you run your Verilog simulator with all the display statements. Remembering, of course, that there is some indeterminacy in what gets executed first and second when both things have got equal priority. But that's the way to practice and learn. You compare your answers with that of an actual Verilog simulator, and you fill up your code with lots of display statements.